I found these proofs a bit aggravating, as you'll hear. All right. Proposition 11, Book 3 says, if two circles touch one another internally, which is a kind of R-rated statement in Euclid, and their centers be taken, the straight line joining their centers if also produced will fall on the point of contact. Alright, so the diagram's as follows. Let's try a bit better than that. There's one circle. Here's another circle. They touch. It's internal to the first circle. They touch at A. Well, yeah. Sorry, let me try again. Make it larger. It's one circle. Drawing a tangent is not easy. Okay. There's another circle. They meet at A. So let's call these circles, I really don't quite get the reasoning for these names, but one circle is ACB, the other circle is going to be ADE. D actually has a meaning, but we do use it, B and C do not. Anyway. So let me put up here the labels. So F is going to be the center of ABC, the large circle. G is the center of ADE. D is going to acquire a meaning in a moment, but let's just let it be. Okay, so of course, like with many of these diagrams, we need to draw them in a way that doesn't actually make sense on purpose. But let's do something semi-reasonable. So F is going to be the center of ABC, and that's G, the center of ADE. I'm going to have to change my mind about the position of D. Make this somewhat sane looking. Well, make it a little bit less sane. Of course, the contradiction is the fact that I can't draw the picture, right? So G is the center of ADE. We're going to produce that line joining their centers, FG. It's going to go to some point on the outer circle, and the claim is that that's the point of contact A, and we're going to suppose for a contradiction that it is not A, and that's where the D comes from. So in some weird way, like the internal circle is being labeled by a thing which is actually not a valid labeling, because that's exactly the contradiction that is in the proof. So like this is not a reasonable way to refer to this circle, but whatever. Proof. Okay, so the claim is that FG, if produced, meets the circles at A. For if not, My translation says, but if possible. I do not really understand what that's referring to. I think it's just the hypothesis that's going to lead to the contradiction. So if not, so let it fall as FGDH. So I'll annotate the H. It's the point on the outer circle. With D, H, and A all distinct. I mean, obviously, if it does meet at A, well, I shouldn't say obviously, the next couple of propositions I kind of feel a bit iffy about whether we actually have enough axioms to really but that's fine. So if they're all distinct, then we're going to derive a contradiction. Okay, so let AF and AG be joined. Here, AF AG. Then, since AG, GF are greater than FA, we've cited that proposition enough times, I won't do it here. And FA is the same as FH, right? Because F is the center. Let FG be subtracted from each. That is from this and from this. Then AG is greater than FH, subtract FG, which is GH. Okay, so AG is greater than GH, but AG equals AD, because G is the center of that inner circle. So AD is greater than GH, lesser to greater, because D is on the line between F and H, because the one circle is internal to the other, and that's the contradiction. So this contradiction shows that in fact DH and A cannot be distinct, and A must be the point at which FG, if produced, meets the outer circle. Okay, up to you, Ken.
Thanks, Dan. Touch. So I guess I'll move along, and I won't get the sky projection.
Yeah, too bad. You have to go first.
Okay, so this one is pretty short. It's the external version of the proposition that Dan just did, but the proof is substantially simpler. Not that this proof is all that complicated anyway, but here we go. So proposition 3.12. Okay, so if two circles touch externally, then the line joining the centers will pass through the point of union. So the point where they touch, and the line through the centers, or the line joining the centers, the centers will pass through the point of union. And as usual, the diagram is the most difficult part. We have to draw the diagram in kind of a wonky way. And I think think I figured out how to do this. So you draw it like this, and then the other circle will just have to be like some egg-shaped, potato-shaped thing. And the centers are going to be here. So we're going to call this F and G. Oh, that's G here. I'm going to join, no, hopefully, yeah, we got it. I'm going to join these centers, right? I'm going to call the points of intersection with the respective circles C and B. So C is here and B is here. Of course, we're assuming that, I guess I forgot to say that. We're assuming that, the contrary is true, right? That the lines through the centers of these circles do not pass through the point of union. So, so this is what this diagram shows. And the point of union, the point where they touch, we're going to call A, right? And then we're going to join up the thing, the centers with A, and we get a triangle. Okay, so once we have a triangle, we can do stuff. So, so the proof. Or maybe I'll put the proof on the next board. So the proof is that we assume the contrary. Right, and we let FG, right? Well, maybe I should say let F and G be centers of the circles, and FG, right? And assume, does not pass through the point of union, right, which we call A. Right, and of course C, and I won't write this down, but C and B are the intersections of this line FG with the circles F and G. Okay, and so so then since FA is equal to FC and GA is equal to GD, right? So these are
D. What's D?
Oh, D. Did I say D? It should be B. Thanks.
Yeah.
B. Thanks. So the radii of circles are equal. Right, so FA and FC are both radii of the circle with center F, and GA and GB are both radii of the circle with center G, right? And this gives we get FG, right? So FG is the line joining the circles, is actually greater than FA plus AG. Why is that? Because FG, right, is actually made up of FC and GB plus some stuff, some extra bit of line in the middle. So FC is part of, or the FC and DGB is actually a part of the line FG. And so because these line segments are equal, we get that FG is greater than FA plus AG, which is a contradiction. Because contradiction, right? Well, maybe I should say contradicts the triangle inequality, which is proposition 1.20. Yeah, so this is a little bit simpler than the one that Dan just presented, but it's the external counterpart.
Yeah, exercise for reader. Why can't circles touch in two places? So like the definition is like we would say, I think, a little bit confusing about whether it's global or local. So it says circles that touch one another which meeting one another do not cut. So that's like a local condition, right? It's like they touch but do not cut. But it's sort of, I'm not sure we've proven that circles can't touch twice and be distinct.
Yeah, not that I recall. I mean, I think last week or 2 weeks ago, I was slightly worried about circles intersecting in, fewer than, what was it?
Yeah, that was the proposition 10. Yeah. I guess
what could happen here is that if C and B are actually the same point, it doesn't work.
Yeah. I mean, I guess this actually settles that, right? So, what does it? So if two circles touch one another externally, suppose they touched in two places, then the straight lines joining their centers will pass through the point of contact. So, if there were 2 points of contact, well, yeah, actually it's begging the question a little bit, proposition 12, right? Because it's deriving.
So this will prove that there's only 1 point of contact, but we assume that there's only 1 point of contact to begin with.
Something to think about. Okay, what are we up to?
13.
13, yeah. Okay, so did you detach already?
Oh, sorry.
Yeah, no problem. Okay. Okay, a circle does not touch a circle at more points than 1. Whether it touch it internally or externally, which is, of course, what we were just discussing.
Right. I guess this uses the previous 2 propositions.
Yeah, so I'm flagging my point of disgruntlement, I guess. Okay, but let's give the proof. So I guess there's 2 cases, right? Whether they do it in one diagram, though. You could have multiple points of contact internally or externally. So let's consider first the case of a circle internal to another circle touching it at 2 places, which, yeah, this is the tortured diagram I was referring to in the Discord. One thing I think is amusing is that we would never do this today, right? Or at least we tend not to try and draw things that don't work in the way that Euclid does. Okay, so proof. For if possible, and again considering the internal case first, let the circle ABDC touch EBFD internally at DB, which are distinct points. Okay, I need a letter A. A is going to have a meaning later. ABD and EBD. EBFD. That is bizarre. Yeah, there's no reason to involve the F. I do not agree. So let's just call it EBD. All right, so that's the hypothesis. Let G be the center of ABDC, H the center of EBD, join G to H, and this line must fall on both BD by the proposition we just proved, which is fine. You might worry that we kind of use the uniqueness or something, but anyway, I mean, if you look through the argument, it's valid. But my diagram makes this quite awkward. Well, nobody said lines have to be straight, right? If we're going to draw impossible things, then we have precedent for drawing non-straight lines as straight. Yeah. Okay, so that's the story, right? So that's BGHD. Since G is the center, BG equals GD, despite appearances. Therefore, BG is greater than HD. Yeah, I mean, obviously we need to choose G to be the closer one to B or something, right? So let's think this through for a moment. So we have circles touching internally. We suppose there's 2 points. G is the center of the greater circle. H is the center of the smaller one. So start from G, produce a line from G to H. I mean, could you produce it from G to H, keep going, and hit both B and D? So that they're on the wrong side for this picture. Well, D is a point on the outer circle, so that line would have to meet the outer circle at 2 points traveling in that one direction, which is clearly impossible, but that's a little bit picture-based reasoning.
Yeah.
I think it's fine because if it did that, then there'd be a contradiction with the proposition that says that the line connecting 2 points on a circle is internal. So proposition 2, book 3. So if B and D were on the same side of H on this line, then you'd get a contradiction with proposition 2 because whichever one was first, you will have left the circle, but you would also have to stay within the circle to go between those 2 points by proposition 2. So proposition 2 justifies drawing the diagram as it is. Of course, B and D, you could swap them. The labeling is irrelevant, but they are on opposite sides. So we may as well, without loss of generality, arrange it as shown. And therefore, BG, I can indeed take that to be greater than HD. Okay, back to the argument. Therefore, BH is much greater. I love it whenever Euclid says much greater than HD. Just means using transitivity, right? So BH is greater than BG, which is greater than HD. So BH is greater than HD. And since H is the center, this is a contradiction. Okay, that's quite nice. So that handles the internal case. Maybe I'll just try and squeeze the external case down here. So in the external case, you've got a circle touching at 2 points as so these are supposed to be touching, right? So not cutting. And the contradiction is kind of obvious. We join A to C by a line. That line has to be internal to both circles. So if AKC touches ABDC at distinct points A and C, then joining AC, this line lies inside both circles. Proposition 3.2. Yeah, then I'm maybe not exactly clear on on this. So it says some nonsense about 2 points being taken at random. The usual complaints about this words, but okay, so it uses proposition 2. It fell within the circle ABDCD and outside ACK. Yeah, this is the part I don't quite follow. So it's a contradiction because the line AC has to be both inside ACK and outside. It has to be outside because these circles only touch at A and C, and if it were inside, it would cut, which seems to me to be actually like a more refined definition of cut, right? Then, like, I don't actually, it's not like the term cutting a circle isn't actually somehow completely characterized, it seems to me. So what does cutting mean? It sort of, like it means that at the point A, some points on the circumference of the one circle lie within the other, right? So like to cut is a local statement at a point about some points of one circle lying inside another. And I guess the suggestion is that since AC is internal to AKC, it can't be that all the points on AKC, like none of them lie within the other circle, because you could slide that line along the circle a little bit or something. Yeah, so I'm not in. I think we need a little bit more argument. So I'll sketch just an idea that comes to mind, which is bisect AC, call it T, and draw a line from the center of AKC through T that meets the circle AKC to this point, and we'll have a contradiction if that final point I marked is actually internal to ABD. And the idea is that, well, if the line AC is internal to ABD, or maybe just the bisection point is sufficient. Or yeah, maybe that's sufficient. Like T is definitely a point inside the intersection of both circles, right? Which seems like it must contradict touching, but touching and cutting seem like local things that are conditions at A and C. And so it's not clear from the definition that just having T internal is a contradiction there. So yeah, I think I'm a little bit confused about what touching and cutting actually mean and whether they're global or local conditions. So I feel like I don't actually completely buy the contradiction as stated.
I always I always thought of it as local conditions, but I guess that doesn't give you the contradiction because we haven't said anything about going from local conditions and having points elsewhere in the circle being internal, external, something else.
Yeah, so I think if we take it to be a local condition, then we can say something like, if they touch, then if you any point really close to A, like I start saying words like really close, right? Like if I was taking a point here, I could join it to the center and somehow argue that that is actually inside the other circle, which contradicts cutting. So I think it would be relatively easy if we settle on a proper definition of cut versus touch to augment this proof to complete it. But at the moment, I don't feel like there's any point to doing that or attempting that without shoring up the definition. So yeah, I feel like actually we're missing a complete characterization of cut versus touch, perhaps. So that's a bit of a squib ending, but that's the end of the proof. That's supposed to be a contradiction on the grounds of what I just sketched. I guess, maybe if I remember, I'll try and think more about or look up what later authors did to characterize cutting versus touching. I mean, in modern terms, what we mean by a cut is like a transverse intersection, right? So we would say something about tangent lines and so on, which of course we don't want to do. So it's not like we don't know what to say, but in the context of Euclid, we don't say it that way.
Right.
Okay, I guess we'll leave it at that.
Cool. Yeah. Thanks, Dan. I think next week, 14 will probably take, maybe we'll just take most of the half hour.
Yeah.
Cool.
All right.
All right.
See you then.
Later.